Our first speaker today is Professor Sergey Oblezin from BIMSA, and the title of his talk is Automorphic L functions and Hecke-Baxter operators. Let's welcome.
Thank you very much for introduction, and I'm very thankful to organizers for inviting me to give this talk. Mainly, I would like to introduce a long-term project that I have been doing more than 20 years, and so the main idea of the project is representation theoretic approach to problems in number theory. And it was, this approach was run by many famous mathematicians in 20th century, probably starting from 19th century. And mainly the main point was using methods of harmonic analysis and representation theory applying to problems of number theory. And I would like to emphasize here the central role of spherical functions. And the key examples of spherical functions here, I mean that it is Whittaker functions and Eisenstein series that I will mention in my talk today. So mainly like Whittaker functions, they are Fourier coefficients of Eisenstein series. And but there are many more spherical functions appearing in number theory, and it is a much larger picture. But also I would like to, I put these areas of maths and errors on purpose in such a way so that it will be natural to complete the symmetry, and the main feature of my approach is that it is fulfilled, this scheme is fulfilled with mathematical physics. And so in my research, the main goal is like transferring methods and constructions from mathematical physics and apply to problems in number theory. So for today's talk, it is a part of a big project, and I will be focusing on transferring methods and constructions of quantum integrability, quantum integrable systems, area of mathematical physics, and applying to Langlands program. So this project has started. Actually, you can see it is a talk that I gave on December 5th, 2007 in Princeton, and it has, you can see the title, Baxter operators and L functions. And mainly, like today, I will report on the development and progress within like 18 years or 17 and a half. So first, so in my talk, I will, of course, first introduce the very first paper, which was published in 2008 and that I was reported on the previous slide. It was just a seminar abstract, and three recent papers. So there are many more papers between 2008 and 2025 this year, but in my today talk, I would like to focus on these ones. All these papers are, it is a joint program with Anton Gerasimov and Dmitry Lebedev. So we have this long time collaboration, and so this is the project. The key point, so this is the plan of the talk. So as I have said, first I will introduce you the point of the starting point and problem of this project, how it appeared, from which question. Then I will, so the second item, it is just the result back 17 years ago. And items 3 and 4 It is constructions of Hecke-Baxter operators for spherical and non-spherical principal series representations. I will focus on real general linear group today only. And in the final talk, in the second part of my talk, I will focus how the Archimedean considerations, I mean, of the real group can be extended to the Baxter operator, to the construction for automorphic forms that are global. So this a kind of yes, approximation, you can say, from Archimedean place to the global case. So let me first remind you the setting. So we have the group, general linear group of reals. As usual, B, we have a Borel subgroup. And you can think of it as a group of lower triangular matrices. N is the unipotent radical, so it is a maximal unipotent subgroup. So lower, strictly lower triangular matrix with matrices with units on the diagonal. Then A denotes the positive part of the maximal torus. So maximal torus is a diagonal subgroup, subgroup of diagonal matrices, and we consider subgroup of positive elements. Then obviously we need to also have signs of elements of the diagonal, and this is the subgroup M, which is you can it is a finite group which can be identified with intersection of the Borel subgroup and with the orthogonal, which is maximal compact subgroup. So this is the standard setting. And next, I would like to just introduce principal series representation. So this is an infinite dimensional representation of the general linear group. So it is induced from character high, epsilon gamma of the Borel subgroup. Here is explicit form of the character, and gamma and epsilon. So gamma are real numbers, so that here you can see the exponent of the diagonal entry is purely imaginary and shifted by the Wales vector rho, and epsilon are signs. So because A can be here just a diagonal entry, so here we take sign, put it in a character separately, and the absolute value of A, which is positive, is an element of subgroup A. Yeah, so this is the standard notion of the induced representation, and the group acts on the right. So we have equivariance, B equivariance condition from the left, and the right action of the group. Yeah. Say again. Sorry. Yeah, it is epsilon. Yeah. Thank you. Yeah, so it is a type. So here, epsilon gamma. Yeah. Right. So next, for general values of gamma, the representation is irreducible, and these shifts, they this form of exponent of I, A provides that the representation is also unitary. There is a G-invariant form, so we use this. So now the main notion, so the principal series representation behavior with respect to the maximal compact or to the orthogonal group. So the representation is called spherical if the character is trivial on this subgroup M, which means that all epsilon are zero. So the original character from which we induce doesn't depend on signs of the diagonal entries, and this is called spherical principal series representation. And for Obviously, when epsilon are non-zero, it is called non-spherical principal series. So these are two types of two main types of representations of GLN. Then in the classification problem, so Robert Langlands, he actually associated to a principal series representation L function in auxiliary complex variable S, which depends, so this L function depends on the original representation pi and finite dimensional representation rho of a different group, which is dual group, GL, and it is complex. So original group is over reals, so this dual group is a complex, and therefore, so there is this Langlands correspondence originally formulated in terms of L functions, and it is like associated. So, I mean, he had some arithmetic reasons to associate it in this way, and I don't want to comment on them. And in my talk, so if we choose rho to be standard L+1 dimensional representation, just standard representation of this complex group acting in L+1 dimensional vector space by linear automorphisms, so then the L function has this form. So it is a mainly expressed into a product of gamma functions normalized by pi, and as you may guess if you're familiar with number theory, so of course these factors, they provide certain functional equations satisfied by some global L and Z functions. So this is the construction. So there is a natural question: is there a natural way, well, mainly representation theoretic way, to construct this L function from the original representation pi of the group without, without giving some arithmetic considerations, without using motivic arguments, just purely representation theoretic construction. So the answer is yes, it is positive, and mainly you can think that this is a motivational or informal definition of what is Hecke-Baxter operator. So it is a, it has operator, I mean that it is a one parameter family parameterized by S, this auxiliary complex variable, and it is a one parameter family of elements in the Hecke algebra. And in the case our underlying representation is spherical, then the Hecke-Baxter operators sit in the standard spherical Hecke algebra. But in the case epsilon are not zero and we have non-spherical representation, then it is our construction, recent construction. There is an extension of this Hecke algebra providing a like non-spherical extension, and both Hecke algebras are commutative. So this is the motivation introduction, and are there any questions at this point? So then I would like to continue with just giving first the first construction about the spherical Hecke algebra and Hecke-Baxter operator, and then do non-spherical case and extension to automorphic form. Please. Yes, this is a very good question. So the answer yes, and it is also constructed in our papers, but I don't want to mention it in today's talk. So my point for today's talk that I would like to do the Archimedean case and then somehow extend to the global case, avoiding periodic picture, but it is doable as well. Yeah. Any other questions? Right. So to do, I recall first what is the spherical Hecke algebra. So on our real group, we have Haar measure, or just a standard Haar measure. Then we consider the convolution algebra. So on the space of integrable functions on a group, we have associative multiplication given by the convolution. And when you look at convolution, you can think of convolution of two functions. Also think that actually we have an action of integral operator defined by the function f1 acting on a function f2. So this will be useful to have in mind. And the second remark, that standard construction, that if we have a representation of our underlying group, then we have a representation of this associative algebra defined in this way. And so the representation of G is irreducible if and only if representation of convolution algebra is irreducible. So therefore, this convolution algebra is just the continuous analog, if you like, of the group algebra. Right. So now I recall we have spherical principal series. So here we have 0, and when I will drop it, so I will just write here, just drop epsilon, meaning that it is 0 with the same action. And then in our representation, there is a unique so-called spherical vector, so which is invariant under the action of the maximal compact group and normalized by the condition that it equals 1 at the unit element of the group. And explicit form of the spherical vector is this. So using the Iwasawa decomposition of our group, so NA is the Borel, K is maximal compact. So we write it down like this, define this vector where phi is the original character of the Borel. And so obviously it is K invariant under the action of the subgroup K. Right. So now we have, once we have this unique distinguished vector in our representation, we can define a linear continuous map from underlying representation to the space of square integrable functions on our group, just sending arbitrary vector to the so-called matrix element. So since our representation is unitary, here we have in matrix element, we put the spherical vector, which we know we have, and here arbitrary V. So this gives embedding of our, well, linear continuous map. And so the obviously our convolution algebra will act on the matrix elements in this way. And now the spherical Hecke algebra, it is a vector space of k bi-invariant functions. So functions such that multiplying from left and right by elements of the maximal compact function is invariant. Then it is algebra with our convolution multiplication, and under convolution action, spherical vector and any matrix element with spherical vector are invariant. This spherical Hecke algebra is commutative, and therefore the eigenvalues lambda they define one-dimensional representation of this commutative associative algebra. So this is the standard gain constructions. And now introduce the Hecke-Baxter operator for spherical representation. So we consider this function Qs of G, or family of functions, parameterized by arbitrary complex parameter S. So as you can see, it is K bi-invariant because in exponential we have trace of G transposed, and here we have absolute value of determinant. So this is indeed a K bi-invariant function. Then we know that acting on spherical vector, it is so spherical vector is eigenvector under this action of by convolution of this operator, and it is not difficult calculation, standard calculation with Iwasawa decomposition and calculating integral of GLN of a general linear group with Haar measure gives the eigenvalue that is required. So this is the spherical, the L function, Archimedean L function associated to spherical principal series representation. So this is in this way, as we have discussed, so this is the answer to the original question. So we use representation theory construction applying to our group and spherical principal series representation to construct L functions, L function Archimedean as an eigenvalue of certain family of elements in the spherical Hecke. So this is very natural and a simple construction. So one of the, in particular, one of advantages of this construction is that it gives integral representation for L function, because it is another important question in Langland's program to study properties of these of L functions. There are some conjectures, hypotheses about behavior of zeros of these L functions, and therefore here we have integral representation for it, just remembering that our spherical vector is normalized by condition that at unit matrix, at unit element, it takes value 1. So we have this integral representation for the eigenvalue, for the L function. Right. So now, question, another probably natural question, why it is called Hecke-Baxter operator. So this term came from theory of quantum integrable systems, and I just would like to address this question: why Baxter? So Hecke, it is clear why, but it is this family of elements in Hecke algebra. So that's why it is why Baxter. So as I have mentioned, so we have matrix element. We know it is an eigenfunction of this family of elements in the spherical Hecke algebra. With the eigenvalue, the same doesn't matter for which vector v we put. So now, if we choose a special vector, which is vector psi, it is an equivariant vector with respect to opposite. So I mean n plus, it is a subgroup of upper triangular unipotent matrices. So this is another opposite maximal unipotent subgroup. And then taking this matrix element, it is what is known to be spherical Whittaker function. So it is a matrix element of spherical vector and this what is called Whittaker vector. So it was introduced by Sergey in his thesis, and later on, as you know, was contributed to the book of Jacquel and Glantz and appeared there as well. So Now, in the theory of integrable systems, if we specialize the element G in the matrix element, restrict it to the functions on the maximal torus and specify G to be just diagonal matrix, then this matrix element, Whittaker function, is what is called wave function or solution to quantum G to the system. G, I mean here, group GL, general linear group. Namely, it means that obviously you have action of the universal envelope in algebra in representation and of its center. So the action of center induces provides that this matrix element is an eigenfunction with respect to second order differential operator. So I mean there are for GLN there are arbitrary order. So it is a system of commuting differential operators. So the simplest one, degree 2, gives this well-known differential operator, which is called the quantum Toda Hamiltonian. So the function is our matrix element restricted to the maximal torus is a solution to this system of differential operators, differential equations. And Baxter, Rodney Baxter, he proposed actually in the studying of quantum integrable systems, he first introduced such a notion in special examples. Actually, he not general construction, but certain class of integrable systems, he introduced that instead of studying integrable systems as wave functions, as a solutions, as a system of differential equation, we can introduce a family of integral operators, which is equivalent to the original system of differential operators. And that's why in the theory of quantum integrable systems, this is known as Baxter operators. And I should notice that Baxter actually studied integrable systems that are related to affine, like Hasmoudi Lie algebras, not finite dimensional. Therefore, so from the point of view of theory of quantum integrable systems, this system is very simple, and it is just so it is a very simple system related to finite dimensional just reductive Lie group. So this is comment why it is called Hecke-Baxter. So it one parameter family of integral operators. Any questions at this point? Then I will move on to the non-spherical principal series case. In the case our principal series representation is non-spherical, it means that this finite group M acts non-trivially in our representation. So this is the finite group we identified with a group of diagonal matrices with plus minus 1 on the diagonals. And so the characters of this group are given by characters of this group are given by these L+1 tuples of 0 and 1s. And so each such epsilon like tuple of 1 and 0s defines a naturally character, obviously one-dimensional complex representation of this subgroup M. So now we use the Iwasawa decomposition to identify. So our original principal series representation was induced from the Borel, and therefore it was realized in the space of functions on the coset G over B. So using Iwasawa decomposition, we can identify G over B with K over M and by this map, and introduce the what is called compact model of principal series representation realized in the space of functions on our orthogonal group. Yes, so this is compact model. So the action of the group is a bit more tricky, but convenience is that we are living in the realized representation in L2 over compact group, and we can apply Peterville theory to study vectors in this representation. And in particular, we want vectors that behave nicely with respect to this subgroup M. Right. So mainly we introduce in our representation space the subspace generated by such functions that look a bit scary, but mainly it is the here high, it is, if you remember, it is a spherical vector, and this is just matrix element in finite dimensional representation W, which is direct sum of all fundamental representations of general linear group. Here, the following simple fact is used from Weyl theory, that restriction of fundamental representation of general linear group, real restriction to the orthogonal group remains irreducible. And the second, it means that the second observation that when we take this direct sum, then this space is naturally identified with group algebra of M. Of this finite group. So in this way, so we introduce the again unique vector, which is defined in this subspace as invariant under the adjoint action of the subgroup M, and choose a matrix element where here these two vectors are sorry, here a typo, so here it is not epsilon dash but epsilon, so it is a diagonal matrix element. Yeah, so then the non-spherical extension of the Hecke algebra, it is spanned by such functions where here it is this matrix element and phi is k bi-invariant function, so it is a product of functions elements in spherical Hecke algebra multiplied by the matrix element in the group algebra of M, and this such spherical extension is again commutative algebra, so which is algebra of function on the full diagonal subgroup, not only on positive path. Right. Next, so this is just technical result. We introduce the non-spherical Hecke operator, which is just original spherical multiplied by certain polynomial, again in terms of the group algebra of this finite subgroup, and the result that acting on this vector, it reproduces the required L function with arbitrary epsilon. So this result, so in particular this vector and this operator were recently appeared independently in the work of Bin-Shen Lin and Peter Humphreys. And actually, so I'm thankful to Peter Humphreys who sent me the references. But as far as I understand, none of them consider, I mean, the Hecke algebra, the Hecke algebra construction. And they, I mean, they do it in a bit different motivation. Just instead of thinking of Q as an operator, they think as another vector, such that you obtain L function just combining two vectors. Yes. So now I would like to, after this technical part, just give you simple examples of GL1, and then just see how it works, and then explain the moving to the two other constructions. So first, let us see in the simplest example what we have. So suppose we have consider the case L equals 0, so it is general linear group, just GL1. So obviously the unipotent subgroup is trivial. So the Iwasawa decomposition just boils down to this just diagonal element, and the A is orthogonal subgroup O1. So the spherical principal series means that this O1 acts trivially in our representation. So I just write down this matrix element, which you can think as spherical function or Whittaker function. So it is just because the reducible representation principal series is just one-dimensional. So it is this well-known what is called also unramified character of the multiplicity of reals. I just write it down as a matrix element here. And then the Hecke-Baxter operator for L equals 0, I mean for GL1, it has this simple form. Yes, and that's why I think it's worth to consider it separately. And then its section on the unramified character is quite straightforward, reproducing the classical Euler's integral formula for the gamma function. And here we impose condition on, analytic condition on S to be able to use this formula. So now the next construction is to represent this kernel of this operator, so this function Qs of x, as a matrix element in some other group, which will explain representation theoretic origin of this Gaussian factor. So as you may guess, and many of you, I guess, know that representation theory construction for the Gaussian goes through the Heisenberg Lie algebra. So we consider the Heisenberg Lie algebra, standard three-dimensional Lie algebra with the center C, and then consider the semi-direct sum of GL1 Lie algebra and the Heisenberg Lie algebra, where GL1 acts in a standard way in the underlying space of x, y. And then we pick for positive C and arbitrary real kappa, we use the quite standard representation of the this semi-direct sum. In physics, this algebra, four-dimensional Lie algebra, is known as oscillator algebra, oscillator Lie algebra. So this is quite standard representation. We also take contragradient representation and define two vectors. So one vector phi is a vector with respect to generators x and y. So it is this combination, x minus I, y. And x, it is another vector psi is an eigenvector under the action of generator x, under multiplication of x. Therefore, you may, as you may see, so this vector psi is just a delta function and sits in the dual space of tempered distributions. And the solution to this equation is nothing but the ground state of the oscillator in physics, or this Gaussian exponent. So taking the matrix element, we obtain this, and then just easily fit parameters kappa and c to get the kernel of the Hecke-Baxter. So this is a simple example for GL1. And remarkably, it works quite straightforwardly for GLN in general case, for case of general GLN. So, but we consider here we need to take two copies of the matrix Lie algebra and consider the symplectic form. So we consider this symplectic space and the Heisenberg Lie algebra. So with this as an underlying space of the Heisenberg Lie algebra. And again, consider the semi-direct sum of GL of our Lie algebra GL L plus 1 and this big Heisenberg Lie algebra. So again, we consider the spherical principal series representation of the direct product of GLL plus 1 and consider the representation so that one copy of GL as again standard construction, it is acts from the left and it is marked by L. The other is right action is marked by R. And this is the representation of this semi-direct sum of GLL plus 1 and this Heisenberg Lie algebra. So it is realized in the tensor product of three spaces. So these are spherical principal series of left GL, this is spherical principal series of right GL, and this is a representation of the Heisenberg Lie algebra with the positive parameter C. I mean action of the center, and again realized in the space of Schwarz functions on the metric space. Then we define the in each copy of GL we consider orthogonal subgroup. So again, take direct sum and consider left and right generators for left and right spherical, orthogonal subgroups, subalgebras, and define the analog of spherical vector. Again, you see similar condition here, and plus the action of the generator of spherical. And the solution to this equation is a tensor product of two spherical vectors in each principal series of this parameter kappa. And as usual for this representation of Heisenberg, gives this matrix Gaussian factor. Yes. So then we just the other vector psi, it is defined in terms of gives delta functions, and as a matrix element of this extended semi-direct product, we obtain this type of function, which of course resembles our kernel of the Hecke-Baxter operator for general linear group L plus 1 of the rank L plus 1, but here we have a power of determinant, and here in general we get the arbitrary spherical function of spherical principal representation. So here we need to specify kappa to be one-dimensional representation of GL to get here power of determinant to reproduce the required integral kernel. And the however, I would like to emphasize that these type of integral operators look promising and far-reaching for applying these operators to obtain other types of more general types of L functions, and they are definitely worth to study. Right. So the final part is in the last 10 minutes. I would like to comment about the extension to automorphic forms. So I will consider, again, starting with a simple example of the multiplicative group of reals, I will define the space of automorphic forms as functions of on this double coset, where gamma is a discrete subgroup and K is the maximal subgroup. And then in the case of GL1, our just unramified character of the multiplicative group will work. Definitely invariant under these two subgroups. So the Hecke operators for GL1 setting, they act, so obviously this action of gamma GL1Z, it acts by scaling of the parameter multiplying argument by integer n, and we will arrange those Hecke operators for positive n into generating function. Then, of course, our multiplicative character will be eigenfunction with eigenvalue given by the Riemann zeta function, and again imposing certain analytic conditions on parameter S to provide convergence. So now what is the global Hecke-Baxter operator? Because this is Hecke operators like from a textbook, GL1, in the theory of automorphic forms, and we have constructed like Hecke-Baxter operator before for GL1. Now we would like to merge these two, and we merge them in this way. So it is not just a, product of two operators, but this, although quite simple in the case of GL1, we consider this integral operator with this kernel, and then its action on the multiplicative character, which we consider as GL1 automorphic form, of course, as an eigenvalue reproduces their completed zeta function. So this is the construction, which again can be extended to arbitrary rank, GLN. And I just comment on the case GL2, because it's end of the talk, and to throw on you too many technicalities. So there, we consider this case, so GL2R with again discrete subgroup and maximal compact. So we consider GL2 automorphic functions as functions on this space, which is, there is a map to this space, like moduli space. And then we consider our standard spherical principle representation of our group GL2R, realize it in the space of upper triangular matrices with, again, right action of our group GL2. So this is explicit formula for the action in principal series. And then, so what is the function which is invariant on gamma from the left and k from the right? What is this function? How to construct in representation theory? This is very easy. We just take in our principal series representation two vectors. One vector is gamma invariant, which is this. Another is k invariant, which is this. And take matrix element. Then this function, by this construction, will be a function on this double coset. So this can be done explicitly. Of course, for solving this equation, these two vectors can be found explicitly and obtain explicit form for their automorphic function. So to do it carefully, we use the rigged Hilbert space, so-called rigged Hilbert space introduced by Gelfand. So in our principal series representation, we consider a subspace of so-called test functions, which are smooth vectors, and embedded as a subspace into the space of generalized functions. And therefore, the spherical or k-invariant vector is a smooth vector, obviously, so it sits here. And the gamma invariant vector it is a generalized function and sits in this space. So by Gelfand theory, the pairing in our spherical principle remain working as pairing between test function and generalized function. And so we solving equations, we find these two vectors. And then taking matrix element, we obtain this series. So there, it is not hard. It is yes. I should note here that we impose here the condition to make this series convergent. We need to impose some condition on the parameters of our principal series representation. And because this series, it is a function matrix element K invariant, so we can specify G, so take a projection onto the coset G over K. And by standard procedure, introduce coordinate tau x plus I y sitting in the upper half plane and reproduce from this series the standard Eisenstein series for GL2. So this is the parameterization of G. So any element G via Iwasawa decomposition can be decomposed this and here arbitrary element of K. I mean, given G, K is unity. Right? So the Hecke operators act in the space of automorphic forms in this way. So here we put alpha representatives of this coset in the space of integer matrix with respect to SL to Z. And the representatives can be chosen in a standard way. So this is from the textbook. And again, we arrange these Hecke operators into generating function. And here plus 1/2, if you remember, in the theory of Hecke-Baxter operator, we put here L over 2. So this is L equals 1 case. So then the automorphic form, this matrix element, E, is eigenfunction with respect to this generating function of Hecke operators with eigenvalue product of two Riemann zeta functions. And now we would like to merge this operator with our Hecke-Baxter operator, Archimedean one, that we have already constructed for spherical principles. So the answer is here. I just obviously, because we have generating function of Hecke-Baxter operators, I take union of all integral matrices with determinant n and introduce the following integral term. So here again structure determinant and averaging over some coset representatives of the Gaussian type. And then it acts on automorphic functions in this way, and the Eisenstein series, the automorphic, this matrix element is eigenfunction with the required eigenvalue, which is a global L function to completed zeta product of completed zeta functions. So this is the like main result that I would like to introduce. I mean, it is just recent result. And the work in progress that I comment briefly at the end of my talk. So first, of course, it is, as I mentioned in the beginning, so the Langlands introduced L functions associated using some arithmetic considerations. So the first natural question to study arithmetic properties of those operators that we have considered. Second, of course, it is a global construction of this merging Hecke-Baxter operator with standard Hecke operators for GLN into one integral operators. We have partial results for other classical groups. And of course, the most exciting and interesting, and probably not for tomorrow, I mean, direction is studying analytic properties of the eigenvalues of the Hecke-Baxter operators using methods of mathematical physics, quantum integrability, including beta and zeta. So let me stop here, and thank you very much for your attention.